This is the fourth section in the Applications of Forces chapter 7 in the Applied Year 2 book, and all that's changed from this in the previous section is that we now include moments. So remember, with a static rigid body, we've talked about the forces. So any forces go up equal to forces that go down. Any forces to the left equal to forces to go to the right. It may be that you've got something on a slope, in which case the forces this way equal to forces this way, or the forces this way equal the forces this way. Yeah, if something is on a slope, so we talked about the forces being balanced when we've got this static rigid body. The other thing that we include now is that moments are balanced. Moments are balanced. That means any moments going clockwise will be equal to moments going anti-clockwise. So with each one of these, we'd be drawing some sort of equations or writing some sort of equation. So you get an equation from that, equation from that, an equation from this, and then we can solve simultaneously. And because we can have a maximum of 3 equations, yeah, one for parallel to the slope, one for perpendicular to the slope, and one for moments, you could in theory find up to 3 unknowns. But the key to doing these questions is drawing out a nice clear diagram, putting all your forces on, and what I do as well is actually draw a moments diagram separately, because you can have so much going on in one diagram. That's the first tip. And the second tip is, remember about moments, that it's useful to take moments from the point or from a point with an unknown, because that way you get an equation that's got less unknowns in it, and it just makes solving a little bit easier. So let's start with the diagram. Let's draw this rough ground down here, and we have a uniform rod which is resting on a smooth peg. So let's do that. Let's draw that. It's going to be something like this. There's an angle of 15 degrees here, and we're told that its mass is 40 kg, so its weight is 40 g. Because it's uniform and it's 10 meters long, then we're going to find its center of mass in the center of that. We will also have a normal reaction here, no friction from that smooth peg. We will also have a normal reaction here. Now we can't use the same letter that we used, so we're not going to use R. So next letter in our alphabet, let's just use S. And because the rod wants to slide that way, friction is going to be acting that way. So that's going to be mu S, and we need to find mu, I think, in part B. So part A, we want to find R, the magnitude of this reaction at C. Actually, I should put the letters on. So A, B, C, like that. I want to find R on my diagram. Now, I could look at the forces, horizontal and vertical, but I would end up with equations with S and mus in, and I don't know what they are. Too many unknowns. But if I take moments from A, then the only unknown in the equation is going to be R. Now remember, I need to know the perpendicular distance from A if I'm going to take moments from A. So for R, that's not a problem, because I think in the question it says that it's 8 meters to point C, so that's 8 meters. But we need to know what the size of the other force is for the rod, and that's going to be this component of the 40G, because this needs to be a right angle. So that component in purple of the 40G is going to be, now this is 15 degrees, remember? It's going to be 40G cos 15. Very similar to previous questions that we've done on slopes. So that means that this is 40G cos 15. So I have a anti-clockwise moment, a clockwise moment, because this is all in equilibrium. The anti-clockwise moment, which is 8r, equals the clockwise moment, which is 5 times 40G cos 15. So r is just that lot, 5 times 40G cos 15 divided by 8. So I'll do that on the calculator. Fraction button, 5 times 40G, which we're taking as 9.8, and dividing that by 8, and we get 236.6518 blah blah. Okay, so let's take R as 237 newtons, three significant figures. Okay, part B, the coefficient of friction between the rod and the ground. Now to do that, I will need to look at forces horizontally and vertically, because S and mu S are horizontal and vertical. Now to do that, the S and the mu S are fine, the 40G is fine, the R here is pointing in a different direction. So what we're going to do down here, I'm going to draw that R out like this. So there's the R. What I want to know is this component and this component of R, the horizontal and the vertical. Now this angle here, that's going to be the same as the angle of inclination. You can work that out. Easy angle rule, so that's 15. So that means that this vertical component is going to be R cos 15, and the horizontal component is going to be R sin 15. So that's what I'm going to be using for my horizontal and vertical. So vertical, let's have a look. I've got S and R cos 15 going up, and I've got 40G going down. So there's equation number 1. Going horizontally, I have mu S going to the right, and what else do I have? R sin 15 going to the left, so they're going to be equal and balanced. Right, because I want to find mu, let's rearrange this equation, make mu the subject. So I have mu equals R sin 15 over S. Now I can rearrange this equation here, make S the subject. So S equals 40G minus R cos 15. So all I need to do now is substitute this for S into here, and that will give me mu equals R sin 15. Now remember, we worked out R up here, didn't we? Yeah, so I'm probably going to use the answer button so I get exact answers. So R sin 15 over S, and S is 40G minus R cos 15. So remember, this R here, I'm going to be using the exact value. So let's type that in and see what we get. And typing that all in, I get 0.374819 blah. So let's make mu equal to three significant figures, 0.375, 0.375. 0.75. And remember, when you work out mu, it needs to be between 0 and 1. So check if your answer is sensible. So part A answer here, part B answer here. First thing we need to do is to put on any forces on here. Anytime a ladder, a rod, or a beam, something like that, is on a surface, there's a normal reaction. So we'll call this one R. We'll use a different letter here for that normal reaction. But since the ground is rough, there's a frictional force going that way. Now, why is it going that way? Because the bottom of the ladder wants to slide that way. So the frictional force is acting in the opposite direction to stop it from sliding that way. The wall is smooth, but if the wall was rough, the top of the ladder wants to sort of slide down that way. So if the wall was rough, there'd be a frictional force going that way up, and that would be mu r if the wall was rough, but it's not, it's smooth. So the only other things we need to put on there are the weight of the ladder. Now its mass is m, it's uniform, so it's acting at the center, so that's going to be mg. And then we've got this load which is put here of 2m, so this is 2mg. So we've now got all the forces on that diagram. Let's start by finding the coefficient of friction. So looking at the forces going horizontally, we have R going to the left, mu s going to the right, so R equals mu s. Since we're trying to find mu, let's rearrange this straight away and put mu equals R over s. Let's resolve the forces going vertically. And vertically we have S up and down 2mg plus mg, that's 3mg. So straight away in this equation here, we can substitute the S for 3mg, so 3mg. Right, so now we just need to find R. We can find R by taking moments. Now we can take moments anywhere, but since we just want to find R, it will make things so much easier if I have an equation that doesn't have S and mu s in it. And that will happen if we take moments from A. Yeah, if you take moments where the unknowns are, those unknowns won't be in the equation. So we're going to take moments from A, and I'm going to draw a moments diagram. So this is point A here. So then I've got a distance here up to the line of action where force R is. I'll put this on in a moment so you can see all of this. And then 2mg here and mg. So let's have a look to see how I got this. So I'll talk about the line of action of a force. In other words, which way is the force pointing? So that R force is pointing that way. So yeah, it's pointing up like that. And I've extended it out like that so that I can get this perpendicular distance here, the one in light blue. The same with these forces here. I want these perpendicular distances. Now this perpendicular distance here from A up to the line of action of the normal reaction R is the same length as this side of the wall, from the floor to the top of the ladder. It's the same distance, and that's going to be 3a cos, or sorry, sine 60. So 3a sine 60 for this length here. So let's put that in. 3a sine 60. Down at the bottom here, this length from A to the line of action of the 2mg, which is this one. Its hypotenuse is A, it's adjacent to 60, so it's going to be A cos 60. So that's just that little bit there. is a cos 60, a cos 60. And then the distance from A to the line of action of the MG, so from there to there. Now the hypotenuse of that right angle triangle is half the length of the ladder because it's a uniform rod, and this mass is going down the center, from the center of the ladder. So if the ladder is 3A, this is 3 over 2A. So this length is 3 over 2A cos 60. So I'll put that in 3 over 2A cos 60. So I have an anti-clockwise moment here and 2 clockwise moments. Because this is in a limiting equilibrium, those moments are equal. So the anti-clockwise moment is R times by 3A sine 60 equal to the anti-clockwise moments. So that's 2mg times by A cos 60 plus mg times by 3 over 2A cos 60. This can be tidied up. Sine 60 is root 3 over 2. So this becomes root or 3 root 3 over 2 RA equals cos 60 is a half. So we end up with MGA plus 3 over 4 MGA. 3 over 4 MGA, because that's 3 over 2 times a half. Every term has got A in, so they cancel out like that. I want basically R equals something, so I can substitute it in there. So let's do that. Let's make R the subject. So that will be R equals, so mg plus 3/4 mg is 7 over 4 mg. And I want to divide it by this, 3 root 3 over 2, which is the same as multiplying by 2 over 3 root 3. The 2 and the 4 cancel out or cancel down, and that will give me R equals 7 mg over 6 root 3. So this can now go here. So let's now put that in. So I'll have mu equals R, which is 7 mg over 6 root 3. And if I'm dividing by 3 mg, I'm actually timesing by 1 over 3 mg. The mg's cancel out here and here. And let's put our answer over here. So mu is going to equal 7 over 18. 6 times 3 is 18. 18 root 3. And if we work that out, 7 over 18 root 3, 7 root 3 over 54, which is 0.224525. So 0.225 to 3 significant figures. So 0.225. So here's my answer for part A. Part B is one of these things about what assumptions have you made, and state how you've used your assumption that the ladder is uniform. That would be that the center of mass acts at the center of the ladder, and the center of the ladder is this 3 over 2a. Yeah, that's the assumption that we've made for that question. Let's start with a diagram. So we have the wall here, like this, and we have this rod which is like this. One end is A, the other end is C, and it's being held in place by some string here. This is point B here where the string is attached, and it's attached to the wall at point D, and we're told that the rod is smoothly hinged. Now a hinge will always have a horizontal and vertical component to its reaction, so let's call those two parts R and S. So there is no like mu R or mu S. So there's two components, a horizontal and a vertical, and we're going to work out what those are. And then we've got the tension in the string, and we've also got the weight of the uniform rod. It's got a mass of 6, so let's put here 6G, and because it's uniform and the rod itself is 4 meters, there's going to be 2 meters from there to there, and it's a meter in that bit, and the bit that overhangs there is 1 meter. Part A is to find the tension in the string. Now we can find the moments, and if we take moments from A, we might be able to find the tension in the string with just one equation, because if we take moments from A here, then R and S are not going to appear in our moments equation. The hardest part of this is actually drawing what that moments diagram is going to look like. So this is point A here, then we've got a distance of 2 meters until we get to the weight of the uniform rod. Now I've got the tension, and the tension, its line of action is this way, like that. So there's the tension. So the hardest bit of this question is now working out what is that distance. Now on the diagram, that's working out what this is. So let me draw that on in purple. So what we're trying to work out is this length of this purple bit here. That will take us to the line of action of the tension. Now what we've got here is a right angle triangle. Now we're also told, I haven't put it on the diagram yet, that the angle between the string and the rod is 40 degrees. So let's put 40 degrees here. So yeah, we've got a right angle triangle here, and we're trying to find the side which is opposite to the 40, and the length of the hypotenuse here is 3, so it's going to be 3 sine 40 is going to be the length of that. So I'll put 3 sine 40. So we have a moment which is anti-clockwise, a moment which is clockwise. They will be equal to each other because this is all in limiting equilibrium, or in equilibrium. Well, actually equilibrium here, nothing's about to slip or move. So we'll have t times 3 sine 40 equals 2 times 6g. So t is going to equal 12g, 2 times 6g, divided by 3 sine 40. So let's work that out. So 12 times 9.8, and divide that by 3 sine 40 in degrees, and we get 60.984. So 3 significant figures. Let's go for 61.0. So tension 61.0 newtons. So in part B, if we want to find the magnitude and the direction of the force exerted on the wall by the rod itself, we need to work out what these two components R and S are. So we need to work out what these two are. Once we've done that, we can use Pythagoras to find the magnitude of the force exerted, and tan inverse to work out the angle of that force exerted. So to find R and S, we're going to have to resolve horizontally and vertically. Now to do that, the tension force, which is here, we're going to have to work out what the horizontal and vertical components are of that. So we need to work out what this is and what this is. Now we know that this angle is 40 degrees. We know this is the tension, which we've worked out to be approximately 61.0 newtons. So the horizontal part of that is going to be T cos 40, and this side, the vertical component, is going to be T sine 40. So that's what we're going to use when we resolve horizontally and vertically. So let's start vertically. Now vertically going up, we've got the T sine 40 and R, and that will equal the component going down, or the force going down, or the weight going down, which is 6G. So we can rearrange that so that R equals 6G minus T sine 40. Now we'll use the T that we worked out from the previous part. So I'm actually going to use the answer button and do 6 times 9.8 minus answer times sine 40. And that gives me 98 over 5 on 19.6. That's nice. So 19.6 exactly newtons. So that is the vertical component of that reaction of the hinge at A. And let's do horizontal. So for the horizontal components, we have T sine 40 going to the T cos 40 going to the left, T cos 40 going to the left. That's going to equal the force going to the right, which is S. So I can work out S, that's an S there, not a 5. And I'm just going to put in what I had before for T so that I get the exact value in again. And what that gives me is S equals 46.7 newtons. This is the three significant figures, so this is not an exact value. So what I know is that this reaction at the hinge has 19.6 newtons that way, 46.7 or thereabouts that way. So the magnitude of that force, is going to be, do Pythagoras, so 19.6 squared plus the 46, or answer squared. So that will give me square root 19.6 squared plus answer squared, because I've just worked that out. And that gives me 50.66 or 50.7 newtons. And I want to know the direction of the force now. Now, if I have a look at my diagram, basically I want to work out what this bit is. Yeah, so I want to work out that angle. So that's going to be the tan inverse, and this is going to be the angle from the horizontal, the tan inverse of 19.6 over the 46.7. And if I do that, I get an angle of 22.76, so let's call that 22.8 degrees above the horizontal. So always state what your angle is in relation to. Some students, for example, they may have decided to work out this angle here, in which case you'd say that it's an angle of whatever from the vertical. So always state what your point of reference is. It doesn't actually say in the question where they want the angle from, so you should always state that. So highlighting the answers, part A, there's my tension. Part B, there's the magnitude of the force, and there's the direction of that force. Right, so you should now be able to do exercise 7D on pages 144 to 146.